All right, can we all see that? No. Okay, so in this chapter, essentially devoted to series, got to start with talking about sequences. So, and then we'll kind of talk about the differences between them as well. But kind of a motivating example to get us started. So, have this function, natural log of 1 plus x over 1 minus x. Is that something you can find a derivative of? So, not could you do it simply, but that's something you could do at all. I think we certainly would be difficult. But here's kind of what we're marching towards. I would be able to take this and replace it. So it might not seem all these different constant coefficient variable x raised to some integer power. So that's kind of, I would love to be able to find a way that I can turn these any continuous function. Much easier to hear. That's kind of what we're marching towards is basically series that allow us to write polynomials that look like that. So our sequence and series things we've talked about before, dealt with. Okay, so a sequence in very general terms, it's a list of terms or elements using some kind of order. Another way you can think of it, and if anybody's planning to go towards like Math 371, the definition I'll use is basically a sequence is a specific kind of function. So in all your time in calculus that we've talked about so far, Calc 1, Calc 2, you've thought of functions being these things that map real numbers to other real numbers, right? So the inputs I give to these functions are always, they're very non-restrictive. They're just real numbers. Sequences are a lot more restrictive. The outputs can be pretty much anything, but the inputs are basically the natural numbers, 2, 3, 4. So there's these functions that essentially act on positive integers, not just real numbers. Typically, we represent these terms as a sub 1, a sub 2, kind of your catch-all, your default. You'll see us use a so you'll see both of these things to represent infinite sequences. So the curly braces to represent that I'm talking about a sequence. Sometimes you'll also see me use the indices. That subscript of n equals 1 signifies that. So sometimes sequences can start at 0 or some other number. It's usually 1, but if I want to be totally specific, I'll give you that specification there. By default, sequences are infinitely long. I won't commonly use that infinity superscript there to signify that. Series. Sequences are these infinitely long. They have an infinite number of cosmetically expressed. They're very So let's look at a couple. I want to find the first 5 terms of these sequences. You want me to walk? Take a shot at it. How about the top sequence? What is the first? How'd you go 1 over 2? Right. So, and that's to know what the first 5 terms are, you have to know what the first index. So input index, you go to the first value of n is. So 1, 2, 3, 4, 5. We said 1/2, right? And then what? 2/3. You okay with that? So the next one, I'm not telling you where to start. So we can essentially assume that it begins at 1 again. What was that? Can I zoom in? Better? All right. Already asked me what the starting index was for the next one. It'd be 1, right? So give me our first terms there. Negative 2/3. And then 1/3. I don't think it's going to be 1/3. Oh, yeah, right. You simplified it for me. So it should be negative, right? Negative 4/27. I'm going to leave this one unsimplified so I can talk about something else. At this point, are you even so? Are there some of you that aren't even looking at the definition anymore? At some point, and this is going to be very common, at some point, hopefully a pattern emerges. And you start thinking about the items that live in your sequence. So we see that this sequence is alternating between positive and negative values, right? What part of the sequence causes that? -1 to the end. So that's a very common thing. Is that and kind of when you define that's a very common way to get a sequence to alternate. Any other questions here? Yeah, if I don't give you the beginning index, then you can assume anything. Typically I don't. Typically I won't. I won't. I'll specify. One thing I will say about this next one here is never mind. Gets that in a little bit. So now let's write a formula. So I'm giving you a sequence. So basically, I'm giving you the first 5 terms. Can we write an explicit formula that would give me any term sequence? What kind of things do we have to consider here? So yeah, so those are 2 kinds of sequences, right? Arithmetic sequences and geometric sequences. So let's talk about those first of all. What is an arithmetic sequence? Right. So an arithmetic sequence your function. Jason's term of that sequence. Let's look at the sequence. Well, I have that here. whatever the difference is between 3/5 and negative 4/25 is not going to be the same as the difference between 5 and 6. So it's not geometric, it's not arithmetic. Common ratio, I'm not sure what the R squared. Like additive chain. Yeah. A geometric sequence has a geometric sequence. How do we know? So, yeah. We're going to talk about let's test it. What do I multiply 3/5 by to get negative 4/25? Maybe. So okay, so it's definitely alternating. Let's see if I'm investigating this geometric thing first. Because if there is a common ratio, that's going to factor heavily into how we define this thing. So the ratio between the first two terms is going to be negative 20 over 75. So negative 4 over 15. If I multiply that by negative 4 over 25, do I get 5 over 125? No. So it's not geometric. So arithmetic and geometric sequences, those are two types of things. This fits. I'm now starting to realize that I did something. I set an unintentional trap for you. I'm going to cheat a little bit. Now I think this thing actually works. So we need to basically look for some other kinds of patterns here. So somebody said something we can rely on. Somebody said an alter. So what are the things we need to focus on? We have an alternating sequence. What other kinds of things are going on? Right. So the numerator has this arithmetic thing going on with it, right? I believe I can just simply increment it by 1 every time and get a new numerator. Go ahead. Right. It's just the denominator is increasing exponentially or geometrically. It's essentially carry the same meaning. If I multiply the denominator by a certain number, I'll get the next denominator, right? So now how can I bring all those things together? So I have an alternating sequence. I have the numerator increments by 1, and the denominator say has common ratio of 5. So I think all those, are there any other patterns we need to like attend to here? So based on those things, can I write a formula here? How do I account for the fact that it's alternate? Negative 1 to the power of n. Okay, so that handles the first bullet. How about the numerator incrementing by 1? Times n plus 1. How'd you get n plus 1? Okay, so you're saying n's going to start at 2. So that's something we have to keep in mind. And then what's the denominator going to be? Five to the power of n minus, I heard n and I heard n minus 1. Okay. So a couple things I need to define this. There's my formula, but I also need to be specific about something else. I need to say that this sequence starts where? All right. We think this is good. Let's talk about them both. So a sub n equals -1 to the n times n plus 2 over 5 to the n. Yeah, -1 squared is positive, right? So let's talk about the first one. Oh, we need to specify. Actually, this one I'm just gonna call it a sub n because I'm not really doing anything. Not doing anything out of the ordinary to these. Yeah. Why is that? Because the one has to be alternating. So we have two options. I'm going to do what VO suggested and increment that. Does that fix that problem? It should. These sequences are not identical, but are they equivalent? They're written differently, but do they do the same thing? We're convinced they do the thing we want them to do. Okay. So maybe good news, maybe bad news, but the way you is not neat. You have a lot of options. Basically, I could also define this where n starts at -10. No good reason to do that, but absolutely is possible. Anything else? So I want to graph because this is a sequence. I think this is the first one we looked at, right? But one of the things that's kind of that I want to hammer home about the way sequences actually behave and the way they're structured is what they look like when we graph. This thing, can I say that n over n plus 1? Is there a way to manipulate this at all? Not really. Actually, yeah, I can. I can say this is true. I don't know if there's a help, but 1 over 1 plus 1 over n. Basically, if I divide both numerator and denominator by n. So first thing I want to ask here is this, kind of looking ahead. What's going to happen to the sequence if I let n just keep kind of a trend of this? So got two axes here. I'll call this the n axis, the a sub n axis. I know that we okay with that. First of all, the limit is going to be 1. As n gets bigger, I'm going to approach. I'll get arbitrarily close to a sub n equals 1. Is it going to approach from below? Maybe it would be helpful if we knew what the first term was. What's the first term of the sequence? Should be 1/2, right? So n equals 1, then I have this point here. If n equals 2, then what's 2/3? And then 3/4? So it looks like it's going to approach this dashed line from below, right? So are we okay with this graph so far? Basically, it looks like this. But if I have several points, is it okay for me to just start extrapolating like that? Are we okay with that graph? Kind of it violates something about sequence. So that's the one thing I want to make clear is that these things are very different. So sequences are only defined like what kinds of numbers, what kinds of values are good input. So whereas usually you plot points and connect them with a smooth curve, there's no basically you can't do that for a sequence. These sequences are only defined at integers. So basically you just have like a series of these. There is no 4.5 term in the sequence. But as I look at those dots going further and further right, it should get closer and closer to one, which is getting harder and harder for me to represent. But yes, they'll get closer and closer without ever really achieving it. So we just talked about a limit. So a sequence has a limit if, in this case, which is essentially, I didn't use the same language, but that's basically what we just investigated. As n goes to infinity. So when I say as n goes to infinity, what am I really looking to do with my values of n? Basically, what's the first part of that notation? We relate that to this thing we just did. Can I ask about this? What is the limit? Or I'm not gonna read it. I'm just gonna write down what I had up there. Does this thing right here have a value? One, right? So yeah, that's what I'm asking. I think you do know what this says if you can give me that value. What is this notation here? What is this? Right, and that's what I want. Hard to say that approach four. Four is a number. We get closer and closer to it. But what does it mean to approach? Basically, it just as it grows with sequences, which are that's the kind of limit we're going to look at. So we want to know is and we would like to know as large is there a number? So the last one, the answer is yes, right? So a couple of the concepts of integrals, but if that limit exists, you have convergence. Okay. sequence has at most one limit. If it has a limit, that sequence converges. If the limit is non-existent, or you kind of a cop-out definition, but sequence is not converging. So really the question you want to ask yourself is, does the limit exist or does it? That's equivalent to this language. When we did talk about this a few weeks ago with integrals, what does it mean for an integral to converge? What does it mean for an integral? If we divide diverge, just it can't be computed. So same kind of thing here. The real question is, does the limit exist? More formal definition of sequences, I think for now, I'll revisit if we want to. We talked about this one, right? Does this sequence converge? Why does it converge? What is essentially, what's the question you have to answer? Right. So the limit of this sequence was 1, right? As n did what? As n approached infinity, or got arbitrarily large. Sequence goes to. Yeah, so that was the question we kind of. Convergence, divergence. Questions after we look at another couple of examples. So, a few things to rely on for limits of sequences. Let's say we have two different sequences, they both converge, so they both have their own limits, and C is just some constant. Basically, if I have two convergent sequences, and a lot of these will make intuitive sense, but if I have two here, they basically converge to basically kind of the limit of the sum. Basically, if I add these two sequences together, so kind of packed in there too is the difference. I do not care if the limit of the sequence is negative. This also works. If I have a convergent sequence and just scale it by constant, then same holds true for products of the sequences. If the sequences converge, then their product, the limits are even. When you get into if I have two sequences that converge, and make heads or tails of that. Can't apply that law. And also if I exponentiate, so if I raise my sequence to some one thing I do want to ask, so says that I need the Paladin positive and I need the terms in the sequence all. See if I can come up with an example to kind of trigger this. Let's say I have a sequence to the limit as n goes to infinity of a sub n equals 1. Actually, let's make it 2. And what's the limit as n goes to infinity of this sequence? A sub n to the power of 4. What does that have to be? 16, right? So that one, we didn't violate anything. We have a positive power. We have the terms in the sequence converging to a positive limit. But what if terms in the sequence converge to -2? Actually, that's not a good example. I was going to converge as well. Yeah, let me think more about this one and see if I can come up with a good counterexample. Why I need those qualifiers. All right, so I have a sequence here. I need to know if this converges or diverges. So first of all, if I want to know if a sequence converges, what's the thing I'm really investigating? Does it have a limit? Under what conditions? So yes, I'm looking for this limit, right? Does this sequence have a limit? But remember that just like in Calc 1, if you want to look at the limit of a function, you have to be doing something specific with your independent variable. So what am I doing with my independent variable to look for this limit? Right. So yes, not as n approaches any real number. It's got to be as n approaches infinity. So this is what I'm really asking. Does the limit of this function exist as n gets? It's not used for. Here's the tricky thing, subtle thing about Saul's rule that you learn after. Here's one way I'll answer this for you. We graphed one, right? Way too long ago. Yeah. It's not continuous. So it's continuous. Can't really talk about it straight. L'Hopital's rule is kind of out. Here's the thing we could do that, like we will do to confirm. We can make a function that is continuous that matches this. That basically where all the terms of the sequence land on that continuous function. We can do that to confirm when we're done, but we don't need derivative. What's going to happen here with this? The first idea I heard was as n gets bigger, think about what the numerator and denominator do. They're both they both can get there in the same way. Grow in the same way. Numerator's going to grow. So what does that mean about the overall? You have a numerator that's going to have a limit. You have a denominator. Let's say the one grows down. So if I have a number that's growing at a faster rate than the thing I'm dividing it by, what can I say about the limit? Should not exist, right? This thing should go to infinity. Can we look at some terms like way out in the future to convince ourselves here? If n equals 100, what does this thing equal? 100 over the square root of 110? That'll be something like 10, right? What about when n equals 1,000? That'll be 1,000 over the square root of 1,010. I'll make it 10,000 because it has an easier square root to think about. So this will be something like 10. This will be something like 100, right? Not quite as big as 100, but basically, you pick whatever large positive number you want. I can find an n value such that that term of the sequence is even bigger. This thing is not going to do it. So I think I can say that for certain. The limit of this sequence is infinity. So does that mean it converges or diverges? Diverges. Let's say instead I want to look at this function, this continuous function that holds true for all the values of x, which is actually defined for it. By the way, are there any values of n or x where this thing wouldn't work, where this thing would not be defined? -10, but I'm not. Unless I tell you differently, we're not looking at -10, right? So this function, is this a good candidate for L'Hopital's rule? Should be, right? The denominator goes to infinity, the numerator goes to infinity, which means the limit of this thing is equal to the limit of basically the derivative of the numerator over the derivative of the denominator. What's the derivative of x? 1. What's the derivative of the denominator? Yeah, so is that, I'm calling this n, I want x. Is that something I can find the limit of? And this better not approach 0 because we just said it diverged. So let's rewrite. This is the same as limit of radical 10 plus x over 2. Does that diverge? Yeah, should, right? The only place where the variable appears in the numerator, so the numerator keeps growing. So I think we have enough evidence. How about this one? Any first impulse? The instant converge, how come? The numerator's gonna go slower than the denominator. Okay. So here's the prediction on the table. We have the limit as n approaches infinity of a sub n is equal to what? And that's really the question we're answering. It's one thing to say the limit exists. It's not super convincing. If you want to say a sequence converges, yeah, if the limit exists, the sequence converges, but most things you do is tell me what we think we know what. Maybe it goes to zero. If the denominator grows at a faster rate than the numerator, it will tell you that. And essentially, this thing should get smaller and smaller and smaller. It'll always be positive. It should get closer. So this kind of like that's not a great part. Not exactly on the sequence, but I know that I have access to this function that is real valued. Is this a good candidate for L'Hopital's rule, though? Does it meet all the other conditions of L'Hopital's rule? What does the numerator trend to? No, just the numerator itself. So the natural log. The natural log of so as x gets really large, the natural log of x will not. It has no limit. It'll go to infinity. What about the denominator? So this limit is equal to. I'll make it clear for what I'm doing here. Clearer. What's the derivative of natural log of x? 1 over x. What's the derivative of x? 1. Is that a limit that we can say something about? What's going to happen to this limit as x gets very, very large? It's going to approach 0. So converge or diverge, what's the answer? Converge. So it converges, and you can say even more specifically, if it converges, then it has to converge to something. And in this case, it converges to 0. A lot of essentially answering that question. Once it converge or diverge, see you on Friday, or I'll see you upstairs.